Okay, so let's talk about this next section, the graph of a rational function. And I'm telling you right now, this particular section piggybacks off of the previous lecture that was called Properties of Rational Functions. Please make certain you look at that lecture first. Why? Because some of the problems in this particular section are going to ask you to find the domain and the asymptotes and your x and y intercepts, which we already did in the previous lecture for properties of rational functions. This particular lecture is going to focus on us going backwards. Now, they in the past, or in the previous lecture, have given us the actual function. They wanted us to come up with the graph. Well, this section is asking us to go backwards. Here's the graph. Figure out which one of these rational functions actually goes with this graph. Now, I've enlarged the graph to make it a little bit easier on ourselves to see. Now, some of you may be going, how am I going to do this? How do I come up with the function? You know what? The way I come up with this function is the exact same way I graphed it. The first thing I did was found the domain. And that was helpful when I was plugging in numbers, but I didn't really put the domain on my graph. But if you recall, the next thing we did was looked at asymptotes. And the first asymptote we worked with was the vertical asymptote, wasn't it? So let's see our vertical asymptotes. We have x equaling -2 and x equaling +2. So x equals -2 and x equals +2. So you've already started coming up with your function, because remember, these vertical asymptotes come from where? That's right, the denominator, which means if you see x equaling -2, it came from the factor of x plus 2, didn't it? And x equaling +2 came from the factor x minus 2, didn't it? Right? Okay, so one other thing that was helpful to us when we looked at the vertical asymptotes, we also looked at what the graph did on either side of it. So when we look at the -2, we notice to the left of it, it goes up, and to the right of it, it goes down, which means what about the multiplicity of this vertical asymptote? Correct. Since it goes in two different directions, this has an odd multiplicity. Now look at the x equaling +2. To the left of it, it goes down. To the right of it, it goes up, which means its multiplicity is excellent. Means it's also odd. So odd numbers are 1, 3, 5, etc. Well, I'm going to make it easy on myself, because if they don't tell me anything different, I'm going to use the smallest odd number possible, which is 1, which means both of these factors are to the first power, which means the degree of my denominator equals 2. Got it? Okay, so vertical asymptotes are working with your denominator. Understand that. Vertical asymptotes are working with the denominator. Now, let's look at our horizontal asymptote, shall we? Our horizontal asymptote is y equals 2. So we have to remember what that means. Y equals 2 was just a constant. By the way, please don't confuse it with y equals 0. That means something completely different. If I have y equals 2, that means that when I took the limit as x went to infinity of whatever here, it equaled 2. Well, the only way I was going to get a 2 if x went to infinity is if there was no x, right? Which means this thing in the circle had to be just a 2, because the limit of 2 as x goes to infinity is just 2, isn't it? Which means it came from a fraction of 2 over 1, didn't it? And again, if you recall in that previous lecture, this means the degree of the numerator and the degree of the denominator have to be what? They have to be the same, because the x's dropped out. There were no x's left when I took the limit here. The x's dropped out, which means now I know two things. This 2 is a lead coefficient of the numerator. This 1 is the lead coefficient of the denominator, and now I also know the degree of the numerator. The degree of the numerator must also equal 2. So, the horizontal asymptote deals with the numerator. Vertical deals with the denominator. Horizontal deals with the numerator. The horizontal asymptote will tell me my lead coefficient and tell me the degrees of the numerator and denominator. Good? Okay. Well, you know, another asymptote we had was oblique. And if we have a horizontal asymptote, do we have an oblique asymptote? No, we've already discussed that. So we're moving on from there. Okay? The next thing we found were intercepts, right? And as a matter of fact, the one intercept that really made a difference was the X-intercept, because that was also a 0, wasn't it? And in this particular case, my X-intercept is, that's right, X equaling 0. And what's the factor it comes from? Yeah, it just comes from X. Remember, the X equaling -2 came from X plus 2, right? Because you add the 2 back over. Well, if I add 0 back over, that means I have X plus 0, which is still just X. So, something else. Do you notice that the graph at X equals 0 just touches the X-axis? Right? It only touches the X-axis, which means, yep, it has an even multiplicity, doesn't it? So, my even multiplicities could be 2, 4, 6, 8, but I'm going to make things easy on myself. My even multiplicity is going to be the smallest even number we have, which will be 2. Now, do you remember where the X-intercept was always found in that previous lecture? That's right, it was also found in the numerator. So the X-intercept is also dealing with the numerator, which means you just found your numerator. You just found your numerator to have an X squared in there. And now, look at this. The degree of the numerator is a 2, as well as that denominator. The degrees are the same, aren't they? So, you just found your function for this graph. You found your function to be 2x to the second power over the quantity of x plus 2 times the quantity of x minus 2. And if we look back at the problems they gave us, or at the choices they gave us, which one would you choose? Yeah, you would choose D, wouldn't you? Right? You would choose D. They multiplied the denominator together. That's why there's x squared minus 4, and you know you would have gotten that also. Good? Are y'all with me? Okay, loving it. So notice we followed the same pattern we did in the previous section when we were graphing. Asymptotes, intercepts. Got it? Okay, let's look at another problem. Well, this graph is interesting looking. Let's look at it enlarged a little bit more. They want us to come up with the function that goes with this graph. Lovely. Now, here's the deal. I start the same way that I did in the last problem. Got it? What's the first thing we found in the last problem? Vertical asymptotes. Because when we graphed, what's the first thing we find? Vertical asymptotes. So this looks like x equaling -2 and x equaling 4. So vertical asymptote, x equaling -2 and x equaling 4. Vertical asymptotes deal with the what? Yep, they deal with the denominator. So right now I'm focusing on a denominator. So I know one of the factors will be x plus 2, agreed? And I know the other factor will be x minus 4, correct? Okay, but we're not done with that denominator, are we? Good. By no stretch of the imagination are we done with the denominator, because we need to see the multiplicity around those vertical asymptotes. We need to see what the graph is doing. So at the x equaling -2, to the left and the right, the graph is going in the same direction. They're both going up. Is that an odd multiplicity? Nope, because they're in the same direction. This is an even multiplicity. So that means the power on here is going to be the smallest even number that I'm going to work with, which is 2. If they want it to be a different power, then they should say, but I'm going to put the smallest even number. Let's look around the x equals 4. I'm noticing to the left and the right of that asymptote that both graphs are going in the graph is going the same direction on both sides. It's going down. On the left and the right of that asymptote, they're going down, which means it also has an even multiplicity. And again, I'm going to make it the smallest even number possible, which is 2. And those are the only 2 vertical asymptotes. So now you've told me the degree of the denominator. What is it? Yep, it's a 4. Because this would give me an x squared, and so would this one, right? If you multiplied them out. Good? Okay. So, vertical asymptotes, we found them. We found their multiplicity, and that helped me find the denominator of this function. Lovely. What's next? Good. Horizontal asymptote. What do the horizontal asymptotes work with? Yep, it works with the numerator. So, let's go check out a horizontal asymptote if we have it. And it looks like we have a horizontal asymptote right here, right? At x, pardon me, not x, because it's a horizontal line. This looks like y equals 1. So I have a y equaling 1 as a horizontal asymptote, don't I? Okay, what does that mean? Good. That means that when we took the limit as x went to infinity, of whatever here, it equals 1, didn't it? Which means the only way I was getting a 1 is if there was no x's left, which means I have 1 over 1 in the reduced form with no x's, correct? Which means this was a 1 here, which means if the x's canceled out, the degree of the numerator and the degree of the denominator are what? Yep, once again, in this case, they are the same. So I know my lead coefficient in the numerator is a 1. My lead coefficient for the denominator is also a 1. And the degree of the numerator is equal to 4. Lovely. Got it? Okay. Now, if there's a horizontal, are there any obliques? Nope. So I always write this down. Why? Just to make sure I remember to look. It's always a good idea. Okay, and now I have to deal with an x-intercept. The x-intercept comes from where again? Excellent, the numerator. So I'm dealing with a number part 2 for the numerator. Let's see if we have any x-intercepts, shall we? Looks like I have an x-intercept here at x equaling 2 and over here at x equaling 9. I have 2 x-intercepts, one at 2 and one at 9. Okay, so this means it's x minus 2 and this means it's x minus 9, correct? All right, let me look. What's the graph doing at the 2? Yeah, it's crossing. What's the graph doing at the 9? It's crossing. So, since they cross at both of them, that means I have an odd multiplicity, don't I? Which means for the x minus 2, I'm going to have a power of 1. I'm going to make it the smallest odd power possible. They better tell me otherwise. And for the x minus 9, same thing. I have a power of 1, don't I? Okay, now, right now the degree of my numerator is a 2. But it's supposed to be a 4. Oh, nuts. Wait, did we miss anything?
I'm going to erase some of my inking here so we can look. I'm not seeing any other x-intercepts. Are you? I saw this x-intercept and this x-intercept, and because they crossed, they're an odd power, which means they're 1s, right? And you can't assume one of them to be a 3. You can't do that. So here's the deal. You know what that tells me? That I have 2 other x-intercepts because the numerator gives me x-intercepts, except these x-intercepts are not real. And we even did a problem in the previous lecture when we went to find some x-intercepts. We had 2 of them that were imaginary, if you recall. So, let's see. X-intercepts. I have 2 x-intercepts that are imaginary. How do I know that? Because they're not showing up on the graph. They're not, which means one of them is I, and the other one is, that's right, negative I, because imaginary numbers travel in pairs. And as I mentioned, we had this in the previous lecture for properties of rational functions, so go back and take a look at it. Which means I have x minus I, and I have x plus I, agreed? And when you distribute this, you will notice that these i's in the middle cancel. And if you remember, I squared is a good negative 1, which means I have x squared plus 1 in the numerator as well, which gives me the other 2 x's that I need to make a total of 4 up there. Very interesting, this problem. Got it? Very interesting. So here's what you're telling me. You're telling me your final function has the form of x minus 2, quantity of it, quantity of x minus 9. How about I make a better looking 9 there? Times the quantity of x squared plus 1 all over the quantity of x plus 2 to the power of 2 and the quantity of x minus 4 also to the power of 2. So let's go back and take a look at the problem. We had x minus 2 times x minus 9, right? And then we had the x squared plus 1, agreed? So it looks like it's option, let's see, that numerator looks right. It looks like it's option, yeah, option B here. Because I had a vertical asymptote of x minus 2, so it's x plus 2, and x, there it is. That's our answer. This graph was very interesting. It looked extremely complicated, and you're like, how am I going to find the equation or the rational function that goes with it? Notice, we identified a vertical asymptote and even multiplicities. We identified a horizontal asymptotes and the degrees, and then the x-intercept filled in the numerator as well. Cool? Okay, so hopefully this makes some sense to you. You have fun with going backwards, and I'll catch you on the flip side.